All right, so let's look at 8.4, normal distribution. A normal distribution is a symmetric bell-shaped distribution with a single peak. So an example, a rough sketch is this right here, in which your mean or the single peak corresponds to the mean, mode, and median. So we're talking about right here in the middle. All right. And it just represents the distribution of data that's considered normal. So the variation of the distribution can be characterized by its standard deviation. Also, another characteristic of the normal distribution is that the total area under the curve is equal to 1, or in other words, 100%. And so that's going to matter, a little later as we get into our calculation and go into our z-score chart. Um, oh, let me go back here. Sorry about that. So the total area under the curve of the normal distribution is equal to 1, or 100%. All right, conditions for normal distribution. It says a data set satisfies the following four criteria is likely to have a nearly normal distribution. And that's going to matter, as we continue to move forward, recognizing that we have normal distribution. First, most data values are clustered near the mean, giving a well-defined single peak. So when you look at this once again, notice the bulk of your data is going to be near the mean. That's where, and don't forget, mean means average in statistics. So the bulk of your data is going to be near the average. And as you get further and further away from the average, you have less and less of your data, whether you're going to the left or right. In other words, greater than it or less than it. So that's why you have those tails. So the data, number two, the data values are spread evenly around the mean, making the distribution symmetric. So symmetric means, and I didn't mention this earlier, symmetric means that you have this middle point and everything to the right of that middle is the same thing that's happening to the left of the middle. So you have this symmetry. So 50% of your data is to the right, 50% of your data is to the left of your mean. And number three, I already alluded to that one. It says larger deviations become increasingly rare, producing the tails. So, let's look at the average height of a man or average height of men. The average height of men would be right here in the middle, and the most of the heights would be near the average. But as you get taller and taller, less and less people will be as taller and taller and taller than the average. So you have less people, and that's why you have those tails to the right. And then the same thing with being shorter. You get less and less people, the shorter and shorter and shorter you get in your measurement of height, which creates the tails to the left. Right. And then number four, individual data values result from a combination of many different factors, such as genetic and environmental factors. So, for example, height, like I just finished mentioning, genetic, environmental factors um, normally have normal distribution. Mhm. Properties of normal distribution. First thing we're going to look at is the empirical rule. So APP stands for approximately. So approximately 68% of the data is within one standard deviation of the mean. Approximately 95% of the data is within two standard deviations of the mean. And then approximately 99.7% of the data is within three standard deviations of the mean. That's your empirical rule. All right. So we have notation here. We mentioned these symbols in the previous section, but just a reminder as to what we're using right here and what they mean. X is always going to represent your data value. The Greek letter mu represents your population mean. Greek letter sigma. This is lowercase sigma, represents your population standard deviation. All right. And so here we have a diagram that represents those three statements of the empirical rule. Notice our percentages right here. Now keep this in mind, those percentages never change. So we have 34%, 13.5, 2.35, 0.15. And that's the same thing that's happening over here. Remember, it's symmetric about the mean. So what's going on with the right side of the mean is the same thing that's going on with the left side of the mean. So you have 34, 13.5, 2.35, and 0.15. So if you add all those together, you get 100%. All right, so looking at the empirical rule, it says within one standard deviation of the mean is 68% of your data. So in other words, you have your mean in the middle. And if you add a standard deviation to the, and that goes to the right, and then subtract the standard deviation, which goes to the left, 34 and 34 will give you 68% of your data. Then if you go two standard deviations out, in other words, add another standard deviation and subtract another standard deviation, these four percentages, when you add them together, that will give you 95% of your data. Going out three standard deviations, that will give you 99.7% of your data. And then, those 0.15s on their tail ends will add up to finishing it off at 100%. So once again, what's going on down here, that's not 30. That's three standard deviations, 3 times the standard deviation. Same thing here. This is 2 times standard deviation. And then here, that's just your standard deviation, just one standard deviation. So just make sure you keep that in mind. That's not 20, that's not 30. That's just your standard deviation being multiplied twice. All right, scrolling up. Let's look at our first example. It says the mean IQ score of students enrolled at University A is 100 and the standard deviation is 16.1. DET is determined. So determine the percentage of students who have IQ scores within 3 standard deviations of the mean according to the empirical rule. B, determine the percentage of students who have scores between 67.8 and 132.2. C, determine the percentage of students who have scores above 132.2. All right, first we're going to look at the given pieces of information. They give us the mean and the standard deviation. Now, when you go back to your empirical rule, you have your mean in the middle, but then you have values, 3 values to the right of your mean, and then 3 values to the left of your mean. So we're going to calculate those 6 values. And the way we would do that, we look at the right side of my mean. We take our mean and add a standard deviation. That's that first value. Add another standard deviation. That's the second value. Then add a third standard deviation. That gives us a third value. So 100 plus 16.1 is 116.1. Add 16.1 again is 132.2. Then add 16.1 one more time is 148.3. And that will give you 1, 2, 3 standard deviations above the mean. Then to find the left side, those 3 values to the left of your mean, you will subtract the standard deviation 3 times to get those 3 values. So 100 minus 16.1 is 83.9, minus 16.1 is 67.8, and then minus 16.1 one more time, that's 51.7. And that will be 1, 2, 3 standard deviations below the mean. All right. So if I had to fill out the chart, remember what I mentioned before, these percentages stay the same. They never change. The values down bottom will change according to whatever your standard deviation and your mean are. So we have our mean in the middle, that's 100. Then to the right, and I tried to color code it. So then to the right, we have our 3 values, 116.1, 132.2, 148.3. Then to the left, 83.9, 67.8, and then 51.7. So now let's go ahead and answer A, B, and C. So now A, we really didn't need to do that calculation to answer the question. It says determine the percentage of students who have IQ scores within 3 standard deviations of the mean according to the empirical rule. So basically, this statement is based upon, well, the answer is based upon the empirical rule. So you go to the empirical rule, and the answer is right here. Approximately 99.7% of the data is within 3 standard deviations of the mean. And that's why our first answer is 99.7. B, it says determine the percentage of students who have scores between 67.8 and 132.2. 67.8 is right here. 132.2 is right here. So you add the percentages between those two values. That's 13.5, 34, 34, and 13.5. Add them together, and that'll give you 95%. So they can ask you any of those values, and you can just add whatever percentages that are between those values to get your answer. And then the last one, determine the percentage of students who have scores above 132.2. So 132.2 is right here. I can get it right here. And the values above these two percentages. So that's 2.35 plus 0.15, which is 2.5%. All right. So you expect 2.5% of students to score above 132.2. All right. Let's look at a few more things. Let's get into Z-scores. So your Z-score, in other words, another way of looking at it is your standard score. That's the distance a data value is from the mean in terms of standard deviations. All right. So the formula, generally your formula is the data value minus the mean divided by the standard deviation. And here's your symbols for those values, x minus mu divided by sigma. A few other statements about your Z-score. Your Z-score is unitless and has a mean of 0, standard deviation of 1. And that'll make more sense when we look at our Z-score chart. All right. So let's look at an example using Z-scores. Determine whether the Angels or Rockies had a relatively better run-producing season. The Angels scored 773 runs and play in the American League, where the mean was 677.4 and the standard deviation was 51.7. The Rockies scored 755 runs and play in the National League, where the mean was 640, standard deviation was 55.9. All right. So if you follow baseball a little bit, you would know that when it comes to Major League Baseball, there are two different leagues within the league. You have your American League and your National League, and both of them have slightly different rules when it comes to their play. So that's why their mean and standard deviation are worth looking at, because you have a different one for the American League versus the National League. All right. So let's look at finding our Z-score for our Angels, and then find the Z-scores for the Rockies. Remember, the Z-scores, I mean, not Z-score, but the Angels are in the American League. So they scored 773 runs, where in the American League is 677.4 for the mean, standard deviation 51.7. Then for the Rockies in the National League, they scored 755 runs, mean is 640, standard deviation 55.9. So we're going to perform the Z-score for each one of those individually. So here we go. That's 773 minus 677.4 divided by 51.7. That'll give me 1.85 for the Angels. And notice that statement down there, you always round Z-scores to 2 decimal places. Once again, that Z-score chart is going to matter when we get there. And then for the Rockies, 755 minus 640 divided by 55.9 will give you 2.06. All right, so our statements based on the information that we just calculated. So the Angels scored 1.85 standard deviations above the mean. So it's considered above the mean because they are positive. It is possible for your Z-score to be negative. A lot of Z-scores are positive, so that's considered above the mean. The Rockies scored 2.06 standard deviations above the mean. This means that the Rockies had a better run producing year. All right. Let's look at another one dealing with Z-scores. Says the mean daily temperature for San Francisco is 65 degrees Fahrenheit. Standard deviation is 8 degrees. On one day, the high temperature was 49 degrees. What is this temperature in standard units? In other words, what's the Z-score for this? Assuming the empirical rule applies, does this seem unusual? All right, so our given information is over here. Our mean is 65 degrees, standard deviation is 8 degrees. Data value that we are considering or discussing is the 49 degrees from that high temperature. Z-score is right here, 49 minus 65 divided by 8. That ultimately gives you negative 2.0. So according to the empirical rule, 95% of the data is between -2 and 2 standard units. So this would be considered an unusually cold day. All right, so here's just a generic number line, just expressing or re-expressing or reinforcing what we're saying here. So if it's 2 or greater, it's considered unusual. If it's -2 or less, it's considered unusual. But then anything in between is considered normal or usual. All right, let's look at percentiles. The kth percentile of a set of data is a value such that k% of the observations are less than or equal to the value. Kth percentile is denoted by P sub k. All right, sample here. Jennifer just received the results of her SAT exam. Her SAT math score was of 600, is in the 74th percentile. What does this mean? All right, so it just means that 74% of the people who took the SAT or took the exam scored 600 or less, and then 26% scored better. So that's 100 minus that 74. That's how you got 26%. All right. Let's look at applications of our normal distribution. So we already talked about the z-score chart, z-score formula. So let's go ahead and move up to the z-score chart. Okay. So let's say my z-score ended up calculating out to 1.23. Let's say so then I want to go to our z-score chart and pull the chart value, and we'll talk about what the chart value means in a second. But the way this is set up for us is that when you go to the chart, you have the 10th up to the 10th place. On this left column, negative 3.4 is the lowest value, positive 3.4 is the highest value, and that goes to the 10th place on this left column. And then on the top row goes to the hundredths place. So it goes from 0.00 to 0.09. And what we're going to do is, if my value is 1.23, I take the 1.2, go to the 10th place, find it over here, then take my value that's furthest to the right, my hundredths place, find it up here. That will be the 3. And then where they meet will be the value that I pull from the chart. All right, so 1.2, and then the 3 is up here. And where they meet is what I pull from the chart. So let me show you how this looks. All right. So the chart that I'm going to give you, well, I could have left that up there. The chart that I'm going to give you is 2 pages. So the first page are negative values. So it's negative 3.4. You see negative over here, negative 3.4 to 0. And then the second page are positive values. So let's go from 0 to positive 3.4. All right. So if I'm looking for a positive 1.23, I go to 1.2, which is right here, 3, which is right here, and then where it lines up. Where it lines up, or that will be 0.8907. All right. So if you will see that when we go back to the notes, that's the number I wrote down. So same things if I had a negative value. Let's say if I had negative 0.58, I will look for negative 0.5 over here, which is right here, 8 here, and then where they match up, line up, that's the value that I pull from the chart. In this case, that's 0.2810. All right. So that's how we pull the value from the z-score chart. Now, notice also when you look at this diagram up here, it says my z-score is right here, and then shaded everything to the left. Same thing here, z-score is right here, shades everything to the left after that. So we're going to talk about what that means in a second, but I just wanted you to see what I'm talking about before we go back to the notes. All right. So notice that's what I have here, 0.8907. That's the value that we're pulling from the chart. Now, that diagram, it had our z-score and then it had everything shaded to the left. What that's telling us is that that value that I have right here that represents everything to the left of or less than that z-score or that data value that we have. So this 0.8907 represents the proportion of data that will be less than the value that I have or less than the z-score that I have. So the chart will always give you less than. That's what I wrote right here. The chart will always represent what is less than or to the left of your data value. Once again, your chart will always give you less than. Now remember, everything under the curve is equal to 100, or in other words, equal to 1. So to find out what's to the right of or greater than, you subtract the chart value from 1. So it gives you what's on this side. If you want to know what's on this side of the z-score, you subtract that value from 1. Subtract that chart value from 1. To the left of means less than, to the right of means greater than. All right. So let's look at the next example. So when it comes to these z-score charts and the z-score itself, we have 3 different scenarios that we're going to come across. And you're going to see them in a second. And so all we need to do is hold on to how we handle these 3 scenarios and look for those keywords. And we should be good when it comes to actually finding the answer to the problem. So a pediatrician obtains the heights of her 3-year-old female patients The heights are approximately normally distributed with a mean of 38.72 inches and standard deviations of 3.17 inches. Determine the proportion of the 3-year-old females that have a height that is less than 35 inches. All right, so the first thing we do is recognize the given information. So it's 38.72 for our mean. Standard deviation is 3.17, and the data value in question here is 35 inches. Then we plug that into our z-score formula, 35 minus 38.72 divided by 3.17. That'll give you negative 1.17. Take it to the z-score chart. That means negative 1.1 will be on that left column, 7 will be on that top row, and they meet up at 0.1210. All right. So the chart always gives less than. So in this case, we're going to use the chart value because that's what we were looking for, which is less than. So the proportion of the pediatrician's 3-year-old females who are less than 35 inches tall is going to be 0.1210. 0.1210. So now also, if you needed to, or you were asked to convert to a percentage, all you would do is move the decimal 2 places to the right, and that would be 12.1% of the 3-year-olds would be less than 35 inches tall. All right, let's look at the next one. So using the previous problem, find the probability that a randomly selected 3-year-old girl is taller than 35 or 37 inches. Still on that 37 inches. All right, so that means our mean is still the same, standard deviation is still the same, but this time our data value in question is 37. So you do 37 minus 38.7172 over 3.17. That gives you negative 0.54. Once you have your z-score, you go to the z-score chart. Negative 0.5 on that left column, 0.04 on the top row, and that'll give you 0.2946. So the chart always gives less than. We mentioned that before. Now to find greater than, we're going to subtract the chart value from 1, because remember, that's what we're looking for. Taller than is another way of saying greater than. So 1 minus 0.2946 is 0.7054. So let's look at the third scenario using the previous problem. Once again, find the probability that selecting a 3-year-old girl that is between 35 and 40 inches tall, inclusive. All right, so the first thing we do is recognize once again our given information. Our mean is 38.72, standard deviation is 3.17. Data value, we have 2 of them this time. So our first data value, I call the X1, that's 35 inches. Second data value is 40 inches, that's X2. Convert both of them separately to z-scores. So there's 2 different times that we use the z-score formula. First time using 35, you'll get negative 1.17. Then plugging in 40, you'll get 0.40. And of course, that's a coincidence that you got 40 and 0.40. Take them both to the chart. Negative 1.17 will give you 0.1210. 0.40 will give you 0.6554. All right. So just to give you a visual, give you a little diagram right here. So you know, when the z-score 1, it represents everything to the left of z1. That chart value for z1, I should say, and then the chart value for z2 represents everything to the left of z2. So if I wanted to find out what's between Z1 and Z2, I would take this purple and subtract it from the green. And that will give me what's in between Z1 and Z2. So that's what I have right here. To find out what is between your two values, you'll subtract the two chart values. So notice we're not subtracting Z-scores, it's subtracting the chart values. So after you find your chart values, then you subtract those. And that'll be 0.6554 minus 0.1210, which is 0.5344. All right. So just a quick summary of our three scenarios. So you're going to have keywords that's going to let us know that we're dealing with the scenario of less than. It may just say less than, but shorter, colder, below, under, things of that nature represents less than. And that means when we go to the chart, that value that we pull from the chart will be our answer. Greater than, taller, higher, above, that lets us know that we need to take our chart value and subtract it from 1. And then as far as between is concerned, the only word I could think of for between is between. And we would take our two chart values and subtract them from each other. So those are your three scenarios. All right, so let's do this one more time just to make sure we are good to go before we close out. So based on data from the College Board, SAT scores on the math level 1 are normally distributed. That's very key. So that means we can use our Z-score chart with a mean of 621, standard deviation of 96. So A tells us to find a percentage of scores greater than 600. Our mean is 621, data value is 96. I'm not a data value. Our mean is 621, our standard deviation is 96, but then our data value is 600. So we go ahead and convert that 600 to a Z-score by doing 600 minus 621 divided by 96. Ultimately, we'll get negative 0.22. Go to the chart, negative 0.2 on that left column, 0.02 on the top. They meet up at 0.4129. So our chart value is 0.4129. If we're looking for greater than, then we're going to subtract that 0.4129 from 1, which is 0.5871 or 58.71%. Also, I meant to mention earlier, all Z-score charts are not created equal. The way that I'm telling you to find or use your Z-score chart is based on the chart that I'm going to give to you. You can go Google Z-score charts, and there are about 2 or 3 different types of Z-score charts. If you use them properly, you'll still get the same answer, but you have to make sure you use the proper way of using that chart in order to get the answer. So the way that I'm telling you to use this Z-score chart is based on the one that I'm going to email to you or put in your announcements. So if you go searching for another Z-score chart, whether you Google it or whatever the case may be, you may find one that's different than the one I'm going to send you, and you may have to use a different method in order to find the chart value. If you do it correctly, though, you still get the same answer. It's just that it's a different method for different Z-score charts. The setup is different, so you have to use them a different way. All right, B, find a percentage of scores less than 700. Mean and standard deviation are still the same, but our data value is different. We have 700 now. So 700 minus 621 divided by 96 is 0.82. Go to your chart. So that's 0.8 on that column, that left column, 0.02 on that top row. That gives us 0.7939 when they meet. We were looking for less than, so that means we're going to use the chart value that they give us. So that 0.7939 is our answer. Or if they want a percentage, they'll tell you. So that's 79.39%. Also, make sure you watch how many decimal values they want. They want you around to the 10th place, 100th place, and so on. All right, last one. find the percentage of scores between 550 and 650. So mean and standard deviation are the same, 621, 96, but this time we have two data values. Our first data value is 550, our second data value is 650. So once again, we're going to convert those data values to z-scores separately. So we have 550 minus 621 divided by 96, and that's negative 0.74. Then we have 650 minus 621 divided by 96, which is 0.30. Go to the chart. That negative 0.74 will give us 0.2296. That 0.30 will give us 0.61979. All right, now that we have both of our chart values, we can go ahead and subtract them from each other. That 0.6179 minus 0.2296 will give us 0.3883 or 38.83% as our percentage between those two values. Right. So that's it for 8.4. Let me know if you have any questions. Take care.